All right, so we're going to draw a 30-degree angle. So we know it's a little less than halfway. So we just, any kind of, and we're going to have a point in our first quadrant, XY. We know theta here is either 30 degrees or pi over 6. Okay. So find the tangent of that angle. All right, so the tangent of that angle, if you recall, is opposite. So the opposite side is y, the adjacent side is x. So the tangent of 30 degrees or the tangent of pi over 6 is opposite y over x. Y over x. Okay, and that's all that you're going to put down in here. I don't know why I did it twice. So let's find the tangent of 3 pi over 4 using the unit circle. Let's find the tangent of 3 pi over 4. So remember now, with all of your trig ratios, the first thing you have to do is ask yourself, where is the terminal side of this angle located? Where is the terminal side of the angle located? So 3 pi over 4, you've got to find some way now to envision this, right? So some people, as I mentioned to you with that little idea of dividing your unit circle up into twelfths, that little visual, this would be 9 pi over 12. 9 pi over 12. So you say, okay, up to here, I'm 6 pi over 12. To here, I'm 12 pi over 12. So 9 pi over 12 is midway between the two. So you have to have a way to somehow remember where these angles are located, at least the special angles. So here we are. Here's theta is, or alpha, or beta, or gamma is 3 pi over 4. We know we're in the second quadrant. So what does that tell us about the points, the signs of the points? Huh? Yeah, so we have a negative and a positive. Okay, so we know that the tangent using this unit circle, I want to find the tangent of 3 pi over 4. Okay, so we know that, have I defined? No, not yet. Okay, so what's going to help us here? Anybody figure out what's going to help us find this answer? Make it into a right triangle. So we need to draw our reference angle. So we drop that line segment right down to our positive x-axis. We know that our reference angle here, our reference angle would be pi take away 3 pi over 4. So if I went all the way around like that, I'd be at pi. So pi is the red arc. I'm going to subtract away the blue arc, which is most of the way, and that's going to give me the green arc, which is this angle right here. Oh, sorry, I drew that incorrectly. Control Z. It's going to give me this measure right here. That's my reference angle. So pi is 4 pi over 4. Take away 3 pi over 4. Gives me my reference angle of pi over 4. You should, if you have not started to memorize that unit circle, you've got to memorize it. And really all you have to memorize are your first 3 special angles in that first quadrant over here, right? Pi over 6, pi over 4, pi over 3, the x and y coordinates. Your quadrantal angles you can get just by knowing the radius of your circle, 0, 1, 1, 0, 0, 1, negative 1, 0, 0, negative 1. And then by the symmetry, you know whether to change the signs or not. That's got to be like up here. And I haven't decided yet whether I'm going to allow you to use a unit circle on your test or not. So start preparing yourself, because I may not. Or for part of it, I may not. I may say no notes for part of it and no calculator. Okay, there'll be a section of the test like that, and then you could get another section. So don't think you can just like look everything up. Okay, so you got to start using these over and over again. And I'm not being a jerk. I'm just, these have got to be like your your name by the time you get to calculus. You've got to be able to be very familiar with this stuff. Okay, so pi over 4 is our reference angle. So then what do we know about the values of x and y here? What are they for pi over 4? Square root of 2 over 2, square root of 2 over 2. You like the pi over 4s because they're exactly the same. And the x is square root of 2 over 2, negative square root of 2, and square root of 2 over 2. So the tangent, we're still not done. How are we going to get the tangent? Well, we know that this is our y value. That's this height right here, square root of 2 over 2. And we know the x value is negative square root of 2 over 2. So tangent, remember, is the opposite. The opposite is the y value, which is square root of 2 over 2, over the adjacent, the x value, which is negative square root of 2 over 2. So when I divide those two, I get negative 1. So my tangent is negative 1. Any questions on that? So think about your steps here. You define what quadrant you're in. The minute you know what quadrant you're in, you go up here and put in the signs of your x and y value. Then you find your reference angle, and then you follow what we know about what the tangent ratio means, opposite over adjacent. Okay? All right. Okay, so let's find the slope of the line that makes an angle of theta with the positive x-axis. So we can come up here, back to this, I'm going to erase. So let's suppose I take a line, I don't care, any angle, here we go. I got some point out here called x comma y, here's theta, and I want to find the slope of this line. How do you find the slope of a line? How do you find the slope of a line? Rise over run. In terms of x's and y's, we don't. y2 minus y1, which is the change in your y, right, which is right here. Change in y over change in x. So we know that this distance right here is y. We know that this distance right here is x. So the slope is y over x. Slope of that line is y over x. And you can get that because, look, you could call that point x2, y2, and this point at the origin 0, 0. So y2 take away 0 is the height, y. x2 take away 0 is the horizontal distance. And how did we just define that, y over x? Tangent of theta, right. So the tangent of theta also represents the slope. It's another way to think about it. So the slope is y over x, which is also our definition for the tangent of theta. So the tangent represents the slope that a line makes with the angle theta in the positive x-axis. Okay. All right, so we've got a couple of different ways already now to think about tangent of theta. We can think about the tangent of theta as y over x. We can think of it as opposite over adjacent. So opposite over adjacent is when we're in the right triangle. Y over x is when we're a point on the circle. Okay, and now here's another way to think of it. What can we say about the value of sine theta divided by cosine theta? Let's take a look at that. Sine theta divided by cosine theta for any circle. Okay, so for any circle, we've got some radius of r. I'm going to stick in the first quadrant. Here's r. We got some point. We don't know if this is a unit circle or not. What do we know about this point? That point is r cosine theta and r sine theta. We got that in our last lesson. When r is 1, when it's a unit circle, it's just cosine and sine. But when the radius is something different than 1, we know we have to multiply each of those by r. So if I take the sine of theta and I divide it by the cosine of theta for this particular angle, we get, let's see, do I want to do it that way first? Okay, so if we do sine of theta for any, no, that's not going to work. All right, so let's just do the y over x business again. So here's theta. So the sine of theta is y divided by r, right? The opposite divided by the hypotenuse, y divided by r. The cosine of theta is the adjacent side to theta, x divided by r. You're going to be doing a lot of division with fractions. So hopefully you all know there's a shortcut here. We can go like this because you have the same denominators. So if you have the same size pieces in each one, then it reduces to y over x, which is tangent theta. So this is another way to define tangent theta. Instead of always saying opposite over hypotenuse or y over x, and I said this the other day when we were doing right triangles because I forgot you hadn't gotten there yet. Tangent of theta is the sine of theta divided by cosine. So as two ratios of other trig functions, that's how you can also define theta, tangent theta. Now, when you see this, just a quick arithmetic review. Y over R, if you didn't recognize that, X over R, that you could just cancel those. Remember, any division of any kind of numbers, the numerator always remains the same. Division changes to its inverse as long as you change your denominator to its multiplicative inverse, which is your reciprocal. And so there you get y over x. So you're going to have lots of problems that look like this kind of thing. And you're going to have to simplify. So that's why you need to know that how to deal with fractions. So this would be 1 over the square root of 3 times 2 over the square root of 3, which is 2/3. So just make sure you have that little arithmetic fact somewhere in your homework because you'll be using it quite a bit if you don't already have it down. All right, so here's all the ways we've seen, ways we can think about tangent of theta. Okay, we can think about tangent of theta as, oh, that's definitely backwards, Linda. Sorry. I did this yesterday. I just made a little mistake there. The tangent of theta is y divided by x. If we're on a unit circle, that's the same as opposite over adjacent in the triangle. It's the same as sine of theta divided by cosine of theta. It's also can be thought of as the slope of the line. Okay, so there's 4 different ways to think about your tangent function or your tangent ratio. Any questions on those 6 little problems there? All right, so let's move along. We're going to go back to our unit circle, or any circle here, I guess. We've got a point in the first quadrant with angle theta. We have our height is y, our base is x, and our radius, radius, remember, is always positive, always. So whenever we're thinking about the signs of particular trig functions within the circle, we only have to think about which quadrant it's in, and we only have to think about the signs of x and y. Never about r, because r is always a positive. So how would we define sine in this particular case? What would be the ratio? Y over r, opposite over hypotenuse. And then the cosine of theta, notice I always put this in parentheses, and I just couldn't deal with the formatting anymore in Word, so I didn't put those parentheses in. Okay, cosine, someone else other than Hazel? X over r, right. Adjacent over hypotenuse, and tangent of theta? Y over x. Okay. All right. So now we're going to define 3 new trig ratios. These are your major ones. You know how you have like major stars and major constellations in the sky? You've got minor ones. I don't know who decides what's major and minor, but anyway. These are 3 other trig ratios. And they're all reciprocals of these first three. Okay, so the reciprocal of sine theta is called the cosecant of theta, and we represent it with these three letters, CSC. So the cosine of theta is the reciprocal of the sine. So that would be R over Y. So your hypotenuse is always on the top with these first two, right? R over Y. So now I'm just going to take this thing here and I'm going to write it a different way. I'm going to say the cosecant of theta is the reciprocal of sine theta. You could write it that way. Unfortunately, the letters don't match. You'll see in a minute. Like, it would be nice if this was secant, but it isn't. C, the cosecant, is the reciprocal of sine. The reciprocal of cosine, 1 over the cosine of theta, we call the secant of theta, which is SEC. And that's going to be R over X. And then finally, this one makes sense. Maybe you can do a little research as to why we call, like, it's really interesting to see why we call cosine cosine. What does cosine have to do with sine? Look that up. Cosine and sine. There's a reason. Now the reciprocal of tangent, 1 over tangent of theta, is called cotangent, C-O-T. And that's going to be, of course, instead of y over x, we flip it, x over y. So there's 3 new names for you. Cosecant, reciprocal of sine, secant, reciprocal of cosine, and cotangent, reciprocal of tangent. These are what are known as trig identities, just along with your other 3, sine of theta, cosine of theta, and tangent of theta. So all of these fit into what's called trig identities. All 6 of these. Because an identity is a true statement for all values of your independent variable. So when I say there's a multiplicative identity, 1 times x equals x, that's an identity because it works for all real numbers. X plus 0 equals x is the additive identity because it works for all real numbers. These are trig identities. These are true for all values of theta. So an identity is an equation that's always true for all values of your independent variable. All right, so let's find the secant, a brand new trig. So we got a secant, secant, secant. What's the secant? Secant is the reciprocal of cosine, so secant is R over X. Okay, so what you have to remember is just which one of these belongs to which one of our 3 original ratios. That's all you have to remember. And as long as you can remember your original 3, then all you have to do is invert them. Okay, so secant is the reciprocal of cosine. But before I even do that, and you should get familiar with just drawing little baby pictures all the time of a circle. And we need to always, before I even start the problem, say, where does 5 pi over 6, what quadrant does the angle 5 pi over 6 lie in? Can you draw it on your paper? See if you can get yourself a little picture, and then I'll put it in. Okay, here's 5 pi over 6. My reference angle is, what's my reference angle? Pi over 6, because that's how far it is back down to the x-axis. Okay, it's pi over 6 the rest of the way down, because pi is 6 pi over 6, and I've gone 5 pi over 6, so I only have 1 more pi over 6 to go. Okay, so the secant, so what do I know about values here in this quadrant. I know my x's are negative and my y's are positive. And secant is the reciprocal of cosine. So reciprocals always have the same signs. So if cosine is negative, then secant will be negative. So right before I even start, I know my answer is going to be negative. All right? So secant of 5 pi over 6 is the same as 1 over the cosine of 5 pi over 6. And the cosine of 5 pi over 6 is the same as the negative cosine of pi over 6. I just use my reference angle. So that's 1 over, so pi over 6 is a 30-degree angle. I go out square root of 3 over 2. And now I take the reciprocal of negative square root of 3 over 2. That's negative 2 square roots of 3 over square root of 3. And I multiply top and bottom by square root of 3 over square root of 3. That gives me negative 2 square roots of 3 over 3. And that's my final answer. So this is where all your division comes in here. When you're taking reciprocals, you're always going to be dividing pretty much by a fraction. So you have to invert it and then rationalize the denominator. Now, sometimes in the answer key, I might keep it like this. Sometimes I might put it like this. They're equivalent. I'll always ask you to rationalize the denominator on a test or something. Yeah. Yes. This is negative cosine of pi over 6 the same as cosine of negative pi over 6? Yes. But the location is different. So in other words, all I'm doing here was finding the reference angle, Benny, to be pi over 6. And the cosine here of pi over 6 is positive, right? And I know I'm over here, so I'm going to have negative cosine of pi over 6. Right? If I go negative cosine of negative pi over 6, I'm going this way. And as you can see, the cosine of negative pi over 6, this x value and this x value are the same. But if you were putting it in here, you'd have to say the opposite of the cosine of negative pi over 6. You can't say this with a dash. Okay. Because cosine of pi over 6 equals cosine of negative pi over 6. The cosine of 5 pi over 6 does not equal those two things. It's the opposite because it's located over here. Okay? So you just got to be careful of which quadrant you're in. Other questions? Anything? You'll have lots of practice getting these in your activities. Okay, so the fun is now about to start. I think it's fun. This is like one of my favorite parts of trig, is you now can take all these relationships and the one identity we've already looked at, the Pythagorean identity, which says sine square plus cosine square is 1. And now you can start simplifying ratios like this based on your fundamental trig ratios. You can start doing something called prove an identity. Here's an identity. They're telling you it's an identity, and you have to prove that it's true. We'll talk about that. Sometimes we have to establish an identity. And then this all leads to chapter 7, where we're going to actually be solving trig equations. Okay, so this is all like the precursor for solving trigonometric equations. So there are quite a few relationships between and among trig functions. You'll utilize these relationships to simplify. That's what we're doing here. We're simplifying first. Then we're going to prove, and sometimes you establish a given identity. And then later in section 7.1, we're going to be solving trig equations. All right, so just like when I give you something like this, and I ask you to simplify that, what do? You rewrite it. You rewrite it by factoring it. You use an algebraic property. You know that this is equivalent to this. Oh, no, it isn't. Here, put a plus there. And then we're all right. All right. And you know that the bottom is equivalent to this. So you write the numerator as an equivalent expression, you write the denominator as an equivalent expression, and then you use a property called dividing by 1. Doesn't change anything. So that's what we do in algebra. And that's the same idea here. You want to take the numerator and the denominator, and you want to try to rewrite it as something that it's equivalent to, just like we did here. And then you want to find common factors of 1. Same idea when you simplify, even though it has trig stuff in it, doesn't matter. Yes, it should be. Thank you. I'm going too fast. Okay, so that was just by way of example of what you've already done in life, right, up to now. So let's just take that away for now, and let's do the same thing with each of these. You want to take each of these and somehow rewrite them. So secant of theta, you know, is 1 divided by the cosine of theta. It is the reciprocal of the cosine of theta. So that's a fraction on the top. And tangent of theta is sine of theta divided by cosine of theta. So I'm not going to take the shortcut here because I'm going to keep drumming this into your head. So when we divide by anything, we take that anything, we change division to its inverse operation of multiplication and this to its reciprocal. Lo and behold, cosine over theta divided by cosine over theta is a fancy form of 1. And we get 1 over sine theta. Now the question is, can I simplify that any further? It's the cosecant of theta, right? So that would be your final answer. Okay, cosecant. You could, yes. And then you just have to know what r over y is the cosecant. Yeah. But I would be encouraging you to actually use the real I would encourage you to do it this way because this will be more useful in your identities than the y over the x's and the x's over the r's and the r's over the But yes, you could do it that way. Other questions? All right, so look, we've just created a new identity. Oh my goodness, we have so many identities. We'll definitely get through security at the airport. Just pull out the right one. We've just said that anytime you take the secant of an angle and divide it by its tangent, you're going to get the cosecant. That's another identity. You can do these all day long. Woohoo! New identity. All right. This is really fun. Oh, it's a math teacher saying something's fun, so it can't be fun, right? I love these. Prove the identity. First of all, you have to know what it means to prove an identity. To prove an identity, it's like kind of like when someone tells you the end of a story, or like you watching this murder thriller or something. Or not murder, I meant to say mystery thriller. And someone, comes in and say, oh, did you get to the part where blah, blah, blah happens? And you say, oh, I can't believe you just told me the end of the story, right? You already know the end of the story here. You have to show the trail that leads to the final conclusion. So you have to say, if I'm going to prove this, I have to pick on one side of this equation and manipulate it and show that that side is exactly the same as the other side. So you already know the end of the story. Okay? You do not work on this equation with whatever you do to one side, you do to the other, like when you're solving an equation. You're already told this is an identity. It's already true, and you're proving it. Okay? So the question is, which side of this identity do you start on? And you leave the other one totally alone. You don't touch it. So this comes with a little experience. And the more you do these, the better you get at knowing where to start. But believe it or not, you're going to want to start with your more complicated side, this fraction over here. That's where you want to start. So you're going to leave this first one, the right side here. I don't know, I'm still trying to get this to be okay. You're going to leave this alone. Okay, it's an introvert. It wants to be left alone for a while to recharge its batteries. So we're going to be working on this side only. 1 plus the cotangent. I've changed my angle from theta to alpha just to get you used to some new Greek letters, divided by the cosecant of alpha. There we go. Where do I begin? There's lots of approaches here. Let me go with what you think we should do here. So we're just going to keep reworking this, and somehow we're going to come out with the same as sine of alpha and cosine of alpha. And we could start in different places. I'm just curious to see what you might do. What might you do? No, I don't want to do y's and x's. Just 1 over tangent. Yeah, so that's one approach. So let's look at the different approaches. So you may want to rewrite each of these minor trig ratios in terms of their major trig ratios, right? So it would be 1 plus 1 over the tangent of alpha divided by, and cosecant is 1 over sine. Okay, that's one approach. Now, remember, this is a binomial on top. Always keep more than one term on top in parentheses. Now, what might you do? Sine over cosine. I could, yes, I could, but I'm wondering if we could get there a little easier. So there's so many different ways here to do these things, and some are a little bit easier than others. So I'm going to keep every suggestion we have. I'm going to keep it on here, and then you can decide what you think might be easier. Okay, there we go. That's a suggestion. So that's one. You know how you have those tree diagrams when you're doing computer programs? There's one approach right there. Here's your, well, I should call that number 2 because here's your first approach. What else could you do with this first one? Take this division problem and change it into a multiplication problem. So that's 2 prime, right? Second approach would be my numerator stays the same, and I'm going to multiply it by the reciprocal of the denominator, which is sine alpha. I'm so used to saying theta, it comes right off my tongue. Okay. So let's work with this approach first because it's a little bit easier, right? Not a lot, but a little. So this is just my distributive property right now. So I'm going to do sine alpha times 1 and sine alpha times 1 over tangent. Okay? So I get sine of alpha plus sine of alpha divided by tangent of alpha. So notice I kept my sine of alpha in red. Okay, it's starting to look a little bit like this up here, isn't it? Starting. Okay, it's not quite there though, is it? We got the sine alpha part down, right? So you're halfway home. So I'm going to put that in black because we're halfway home. We're positive right there. We'll keep that all in black. Now what? Yeah, now you want to change tangent and rewrite tangent in terms of sine and cosine. So tangent is sine alpha divided by cosine alpha. We're almost there. Can I add this to my favorites? So we got sine alpha. And now we're going to rewrite this fraction, keep my numerator the same, and multiply it by the reciprocal of my denominator. Woohoo! You see it right there in front of you. Woohoo! I simplify. And there it is. Sine alpha plus cosine alpha. And that's when you get to put, and if you want one, I'll give you some. You'll get to put your big smile face, because you have just proved that identity. All right. Now, let's look at the other approach, because all of this algebraic manipulation is good for us. Are we okay with this? Going in this way. And this is, it's like exponent problems where you can, it doesn't matter where you start, it's just important to do everything and following some property of exponent. And the same thing here. There's no one way to do these. All right, so let's look at the way that Benny suggested here. So Benny said, okay, here we go. I'm going to change everything. Oops, I better change my pen or I'm going to have smiley faces all over. Okay, so what are we going to do if you had something looking like this? And most of this comes down to arithmetic. Calculus craziness is because you have algebra craziness. Algebra craziness might be because of arithmetic craziness. So you've got to kind of conquer your arithmetic to do a good job in algebra, and algebra to do a good job in calculus. So what would you do with an expression like this? Okay, so you're going to say, here I have something on top divided by 1 over sine alpha. So it's going to become multiplied by sine alpha, and then it's going to look almost like this. But when Benny did this, she saved you from having to do this piece right here. So there's pros and cons. So you're going to say, okay, this is the same as the numerator, 1 plus 1 over sine alpha divided by cosine alpha, times the reciprocal of that. The reciprocal of that is sine alpha. Okay. Now you multiply sine alpha times each one of these terms, and you get sine alpha times 1 plus sine alpha times 1 over sine alpha divided by cosine alpha. Okay, this says what? Take the reciprocal of that bottom. That's all it says when you put 1 and you divide something into 1. It just takes the reciprocal. So all I have to do is invert this thing right now. So that becomes sine alpha plus sine alpha times, flip it, cosine alpha over sine alpha. Is sine alpha over sine alpha cancel? And voila, you have sine alpha plus cosine alpha. So pick your medicine. I don't know which way you like better, but that's another way to do it. All right. Now, could I have started any other way? The answer is yes. Is it easier? I have no idea, because what's easier for me may not be easier for you. So let's take a look at this one more time. One more time. So let's recapture this right here, and let's take a look at it. Send to the current page, do something else. What do I want to do with this? Save, choose location, send to new page. Here we go. Okay. So remember, for those of you who had me for 107, when we got to the final part of the quadratic formula and you had stuff like this. Okay, and I asked you to simplify it, and people get lost in simplifying things, and I said, you're adding and subtracting. Oh, why do they, how are you at catching, Jenna? Oh, how am I at, oh, did I hit Irene? I'm sorry. Well, no, I have to be better at throwing. Sorry, Irene, are you okay? All right, sorry. I shouldn't have done that. I know in the old days I could throw things really well. No, all right. So anytime you have plus or minus, you know you have to have the same denominator. So this is equivalent to these two things. So I encourage people to rewrite it as the two separate fractions with the common denominator and then simplify. Same thing can be done here. You have two terms at top. You see that big fat plus sign there. So to squish these two together with this denominator, they had to come from these two things. 1 over cosecant of alpha plus cotangent of alpha over cosecant. I could have started like that by separating them. This is 1 over sine. So what does that simplify to? Look, here's sine. You take its reciprocal once. You take its reciprocal again. Where are you? Sine, back to sine. Or you can invert this and multiply it by 1. Look, we got that first term right away. Woohoo! Look at that. Pretty quick, huh? No reaction? Yeah. All right. Fine. Then cotangent, we're going to work the same way. Cosine of alpha over sine of alpha, because that's just the reciprocal of tangent, divided by 1 over sine alpha. This becomes, keep the numerator the same. Actually, now we can use this shortcut. Okay. Now, the first time I started doing this, did I do that right away? No. I probably went one of the routes we did earlier. With experience, you get a little more confident, and then you're willing to try some different things. But I would strongly urge you, when you have one of these expressions where you have two terms on top and a common denominator, to separate it out. It's usually a lot easier to work with. Okay? What do you think? We're on vacation? Yeah, all right. Well, a couple more days. All right. So I hesitated to put this in. I was going to have this in the first lesson activity, but I thought maybe I'm assuming too much. What did I do? Oh, I did? Okay. Well, I guess I changed my mind. 3, 12, 13. Okay. Look, I was writing this yesterday and grading all those quizzes for you, right? So it was a very busy day off. Ha. All right. Everybody find this? Okay. So let's get started with this, because a lot of your lesson activities is going to look like this. So if we know the value of one of the trig functions at some angle, we can use our identities to find the values of other 5 trig functions. Did I not give you the Python? I know, we're still not done yet. I'm going to do this quick. I'm just going to start it because I want to give you time to work, and I'm tired of talking. To find the values of the other 5 trig functions. So suppose theta is in our 4th quadrant. We don't know what theta is. It doesn't really matter. We're just down here somewhere. There's theta. Okay, we know that the cosine of theta is 12 over 13. So adjacent over hypotenuse. So I should have drawn my circle a little bit bigger, this way. So here we are. Cosine, remember, is your x value, right? We know our x value is cosine. All right. So that tells me adjacent over hypotenuse, which tells me this is 13, this is 12. Okay. Cosine is positive here because it's my x value. What do I know about my y value? Because of my location, what do I know about my y value? Negative, which means sine is negative. Because that's sine of theta. So cosine is positive, its reciprocal secant is positive. Sine is negative, its reciprocal cosecant is negative. When either sine or cosine is negative, tangent is negative, and therefore cotangent is negative. So once I have this established, you can do a little Pythagorean theorem and find out that your y value here is 5. It's actually going to, if we look at the direction, it's going to be negative 5 over 13. That's your sine. Opposite over hypotenuse. From there, you can get all the others. All right. Let me show you the other approach, because you'll want to start using this quite a bit. We know that if you go back to our lesson on Monday, we know that this identity helps us to determine the value of sine or cosine if we know one of them. So we're just told that the cosine of theta is 12/13. So I can put 12/13 in right here and square it and use this identity. So sine squared theta plus 144 over 169 equals 1. Since I'm going to be subtracting two fractions, I might as well put 1 in the form I want, which is 169 over 169, just to make life easy for myself. Sine squared theta is 169, take away 144 over 169, which is 25 over 169. I'm happy to see those numbers because they're both perfect squares. Sine squared of theta, sine of theta now equals plus or minus the square root of 25, 169, which is plus or minus 5/13. But you say to yourself, wait a minute, what quadrant am I in? I'm in the fourth quadrant. Sine is my y value. I'm negative. So it is not that one. Sine of theta is negative 5/13. So you can get sine from your identity. You can get sine from your right triangles. And from sine and cosine, you can get all other trig functions. That's all you need to know. Do I have something with the Pythagorean identity in it? Okay. Yeah, there we are. Okay. So we established this identity in lesson 17. And from this one identity, we can get two more Pythagorean identities. Okay. So if we have cosine squared of theta plus sine squared of theta equals 1, we can get another one because we have the right to take an equation and divide both sides by the same non-zero quantity. So I'm going to divide both sides by cosine squared theta. And then I'm going to simplify both of them. So cosine squared theta divided by cosine squared theta is a nice big 1. Sine squared theta divided by cosine squared theta is tangent squared theta. And 1 over cosine squared theta is secant squared theta. So that's your second or alternate. Your book calls it alternate because I've been reading your book. You too? Good. I'm glad to hear it. Identity. I swear for the test, I'm going to take some problems right out of the reading in the book. I am. I'll take examples right out of the book or something that's in there for a true false something. You read your book, you'll be in much better shape. This last one you can find for your last activity, your lesson activity number 5, by dividing both sides now by sine square instead of cosine square. So that's lesson number 18. I went as far as getting your preview exercises for 19, and that's all I have. It's not there? Oh, boo. Okay, I'll go make a quick copy of this while you're working on your lesson activity. Okay. I encourage you on these problems here to try to move away from your little right triangles and try to use some of your identities. Just so you have, I mean, you can do them both ways. There's always 2 ways to approach these, but you need more practice with your identities. So like here, you might want to start with sine square plus cosine square is 1 instead of drawing your little triangles. But you can draw your triangles. I know some of you are very attached to those little right triangles. I'm just trying to get you to branch out a little bit. No pun intended about, no pun there. Okay, I got to go Xerox that. Hang on. I should have that somewhere. Okay. So I copied something twice. Oh, here it is. Nope. You got your answers though, right? I know what I did. I started with 5960, which was page, I should have started with 60 to 65 instead of 59. If that's what I did. Okay, I'll go get that copied for you. Yep. Oh, you mean off of here? Yes? You can always tell me to slow down. It's the only thing in life I do fast. Everything else is I'm slow as a snail. There you go. Zach. Peter.
Appreciate it.
Yeah. There you go. Gary. See, we got 2 people missing here. Anybody missing out of any of the tables so I can put one in the folder? Okay, Solomon. Okay. All right. Anybody? Everybody's here, right? Oh, sorry, Jackson. Would you put that in the folder for me, Hannah? Okay, Nick. All right, here you go, Richie. Okay. Harry, do you have anything for me to check? Okay. Shane's not here. Peter, I didn't get you, Peter? I got you, didn't I? Yeah. Bella, I gotta get, did I get you, Bella? Oh, no, you already told me, right? Zach, do you have anything for me? No? But you are here, right? Rich, did I get you? I got you, yeah. Okay. Jackson, did I get your homework?
No, but I have it. Something. Yes.
Okay, and then lesson activities and preview?
The previews I don't have.
Okay. Okay. Okay, great. Have you seen Shane or Rob anywhere?
I just don't.
Oh. Is this okay now? Okay. Yeah, you're welcome. Oh no. Oh no. Oh, it's this part. I'm worried that I